evening, everyone, and welcome to the Celtic Club for AIG's Rare Earth Elements Discussion Forum tonight. It is such a critical topic within our industry that we wanted to continue the conversation on the back of the successful seminar held in March this year. I would like to start by paying tribute to the traditional custodians of the land on which we meet this evening, the Whadjuk Noongar, in the locality of Boolaloo, and I pay respect to the elders past, present and emerging. Some brief housekeeping: please switch your mobile phones to silent, and if you need to step out, please do so quietly. Bathrooms are downstairs. You might have all seen near the bar area, and there's also some restrooms just off to the side. The escape is down the staircase. We don't really want that happening tonight. And tonight we're trialling the use of Slido, which is an interactive online platform. So please utilize the QR code, which is displayed on the screen in front of you and was distributed to you via email earlier this week. You can submit questions for the presenters during the presentations, for triage during the discussion to follow. These questions may also be anonymous. The QR code can also be used to sign up for membership with the AIG. Our annual year is July through to June, and this event is just one of the many benefits included. We cannot host these events without the assistance of sponsors. So I'd like to take a brief moment to thank MEC Mining, Lab West, Southern Geoscience and Gaia Geological Services. Without further ado, I'd like to progress to introduce our star-studded cast for the proceedings this evening. Dudley Kingsnorth, Gavin Beer, Ivon Wallace, Richard Granini, who are all subject matter experts in the field of rare earths. First up is Dudley Kingsnorth. Dudley has over 50 years of experience in the international mining industry, 30 of which have been in rare earth sector here in Australia. As chairman of Australian Rare Earths, Dudley's presentation will outline Australia's role in development of global environmentally sustainable rare earths. Dudley, over to you.
Good evening, ladies and gentlemen. The title of my presentation is Every Supply Chain Begins in a Mine. Now, I was going through this presentation with my wife, and she corrected me and said, Dudley, every supply chain does. 50% of our agricultural, they do begin in the ground, but the rest, non-agricultural food products, they do begin in a mine. So apologies for this, not typing it correctly. This is a table depicting a rare earth supply chain from the mine to the showroom for an electric vehicle. Now, there are 8 steps in that, and each of those steps is quite distinct, and there's value add at each step. God bless Japan, they introduced just-in-time inventory. So within the rare earth sector, there are different companies at each stage, and it's very important to understand what is happening further down the chain. Now, for instance, when you're making a magnet, calcium is pretty important that it's minimized. Now, the way the industry is segregated at the moment, if you're selling a mineral concentrate to someone who's using carbonate, you don't get a lot of credit for minimizing the calcium content. By the time it gets to the person, it costs quite a lot of money to remove that calcium. By integrating and making sure you've got transparency in the supply chain, which is what we're doing at Australian Rare Earths, we understand all that. To take out calcium at the concentration stage just after it's less than mine is a lot cheaper than taking it further down the supply chain. So that's one of the advantages of having a totally transparent supply chain, which is what I urge people to do in developing a project. No think just about where you're selling the next carbonate or whether you're selling a separated oxide. Keep your mind on vision, look to the future as to where your product is going to actually end up. 30 years ago, in August, 30 years ago, I made my first marketing trip to Europe. I was project manager, marketing manager for Mount Well. And I went to Johnson Matthey. And Johnson Matthey, at that stage, we thought they were going to buy cerium from us for the production. They ordered a catalyst. The project manager said, now, Dudley, when you come here and make your presentation, we're very keen to see how you're going to minimize the impact on the environment. And that should be a substantial part of your presentation. So I get to the UK and I go to Royston, which is where Johnson Matthey's factories. And I was met at the front door by the managing director. And I went into this big room and I made this presentation to a whole lot of people there. I had a whole lot of questions, particularly from the managing director. And at the end of it, he said, Dudley, I can see that you and Ashton Mining are committed to minimising the impact of your project on the environment. I'm now authorising the procurement manager to negotiate a supply agreement with you. Why am I doing this? I don't want somebody waving a placard at a future AGM talking about the destruction that's taking place at the front stage. Unfortunately, today, most of the people who are producing that original equipment that requires a critical supply chain, they all talk about beginning at the metal. It begins at a mine. And it's up to us, the Australian mining industry, to get off our backside and actually go and talk to the end users more and explain to them that the supply chain does begin at a mine. In Australia, we comply with all the international standards required, environmentally and human rights. And that is quite unique. So it does require a bit of effort, but I can assure you, when you do that, you do get a positive response. At Coppermurra, that's a slide. That's the slide of the mine site. We've carried out a trial mining exercise at Coppermurra to demonstrate that when we mine, we'll be able to rehabilitate the mine after mining has been completed. We're very fortunate. Coppermurra is an ionic clay resource. We only have to drill holes of about 10, no more than 12 metres in our exploration activities, remove the topsoil, and we drill through the overburden and get to the clays. So we carried out this trial mining exercise, and we mined about 3,500 tonnes. We set aside 500 tonnes for some metallurgical test work, primarily at Danstow, and then we rehabilitated, we mixed the overburden, interburden, the low-grade ionic clays, and then put it back into the site. 5 months later, the sheep were grazing on those pastures. When the company was floated, we actually have Neo Performance Materials, who's a major manufacturer of bonded rare earth permanent magnets. They're a founding shareholder. Their CEO has come out to Coppermurra and seen that and said, Dudley, this is quite unique. You can demonstrate not only to the local community, but to the end users of your rare earths that you can minimise the impact on the environment. Can I bring some of my end use customers here? And we said, yes, just give us 2 days notice. And that's the sort of thing that we need to do. If we're going to displace China, we've got to make it abundantly clear that Australia does comply with the international environmental standards and human rights. And that Australia is the ideal partner to have in that first stage. It's not only Australian companies who have operations here in Australia, but it's also the companies that have operations overseas. So if we look briefly at the market, as you'd be aware, total demand for rare earths at the moment is probably about 280,000 tonnes a year of rare earth oxides contained. And of that, 80,000 tonnes of rare earth oxide, those oxides used in rare earth permanent magnets. It's anticipated that by 2030, that demand for those rare earths used in rare earth permanent magnets will double. Now, at the moment, China supplies about 85–90% of those magnet rare earths. And going one step further, with reference to the first slide that I showed on that table, China produces more than 90% of the world's rare earth permanent magnets. There's a huge task ahead of us to even, at the moment, China supplies over 90%. For us, for the rest of the world to even triple their share of supply, it's a huge task. We're going to have to build about 8 to 10 liners. That's not going to happen. We might be lucky if we're producing about 30–40% by 2030, but it's a big ask. Rare earth projects, as you're aware, very high capital costs, and they take a long time to develop. And in front of that, there's a lot of test work, and community relations are most important. So I think it's very useful to look back and see how China has got to the position it's in today. It's done that over the last 50 years. 50 years ago, it was producing just the mineral concentrates and was selling those into the US and Europe for the production of separated rare earths. And then at that time, there wasn't a great deal demand for rare earth magnets. He went into producing catalysts that were used in the glass industry and the ceramic industry. China has progressively moved downstream since then. Then in the 1990s, it went from producing mineral concentrates to the chemical concentrates, and then in the 1990s, separated rare earth products, and so forth. Now, it's achieved that by using export quotas and export taxes and huge incentives for Western companies to build those value-add facilities in China. So China can approach Ford and GM and say, well, if you produce you produce magnetic assembly that brings your seats and windows up, backs and forwards in China, you're going to have ready access to rare earths. You're not going to, the producer overseas is not going to have to pay the export taxes on the rare earths that are exported from China. And we can assure you that we will support that. And there is a lot of integration within those companies in that total supply chain. Well, 10, 15 years ago, there were about 150 rare earth companies in Australia, sorry, in China. And there was a lot less control over those mines than there are today. Now, China primarily chose to reduce that number by two means. One, it enforced the environmental legislation when it was appropriate, not necessarily. But also by introducing production quotas. Over the last couple of years, it's really concentrated those production quotas. So there are now two large companies in China that produce over 95% of the world's rare earths. One is Northern Rare Earth, and that project is based upon the Bayanovo site up near Baotou, where bastnäsite is produced as a byproduct of the iron ore mine. And then down in the south, there's a number of ionic clay projects and also some bastnäsite projects, which produce the heavy rare earths and quite a lot of neodymium and praseodymium. So today, there are just two companies that produce over 95% of the world's rare earths. The story is that the CEOs of each of those companies has a red phone on their desk. And when MIIT, the Ministry of Industry and Information Technology, wants to make a change either in prices, supply, then they go make a phone call to the CEOs and it goes, and that's what happens. There's no doubt that China controls the rare earth sector for its own. We've seen recently over the last couple of years that the prices have fallen. The reason for that is that it really doesn't encourage the development of new projects outside China. So that's why government support is so important, and why it's so important that the producers of rare earths actually have a transparent relationship from their mine, their concentrator, right the way through to the end user. As I've said, it's difficult, but it's worth doing it. I've done it a few times, because fortunately I've been in the industry a while and I know some of these people in the supply chain. But make the effort, because that's how you're going to distinguish yourself from other producers. If you can demonstrate you understand the supply chain, you have those relationships in place. China's resources are finite, and that's why we see at the moment there's a whole lot of cases where China is investing in overseas rare earth projects. And what China can offer It can offer four things. It can offer the technology in the development of a process that will be feasible for the project. It can offer supply agreements, which are very important. It can offer funding, and well, it can offer the test work to develop the process, the test work itself, supply the equipment at a reasonable price, and then supply agreements and funding as well. So that's very difficult for us to compete with that because of that emphasis work by China. This is a pictorial representation of the benefit that China has achieved by waiting and progressively moving downstream in rare earth processing. In 5 years plan before last, China said that by 2025 it wanted to be producing 50% of the world's electric vehicles. It passed that in December 2019. And it wants to convert at least 50% of the rare earths that it processes right the way through to the end product, whether it's an electric vehicle, whether it's a wind turbine, whether it's an MRI. That's the benefit of long-term planning and being able to focus the industry together. The other factor to note is that in the production of rare earths, about 60% of the costs of the chemicals associated with producing those rare earths. In Australia, the mining industry, we have a history where the mine manager is king and he tends to want to do everything himself. To be successful, we have to collaborate and form hubs and work with other people, not necessarily in the same industry, but complementary industries. And a simple example might be, a lot of the solvent extraction takes place with hydrochloric acid. Hydrochloric acid is produced in a chlor-alkali plant. You produce chlorine and you produce caustic. Caustic solves in the aluminum industry. The production of the chlorine and the caustic soda is dictated by the economy. When the economy is depressed, the demand for plastic bowls and things like that falls, and the demand for chlorine falls, and the price of caustic is limited in the price point. So that's an opportunity for a rare earth company and an aluminum refinery to work together, because what they can do, they can offer a contract to a chlor-alkali producer so that all of it is used. So that's one simple example. It is something now that the Western Australian government is looking at in terms of not only rare earths, but other critical materials and how we can pull these industries together and develop hubs so that we can share the benefits of that. And that's basically why Lynas moved their processing to Gabeng in Malaysia. With all those chemicals, it's a lot easier if you just stick a hose through the fence rather than have to put it in tanks if it's in Australia and bring it here and another store it. So we've got to think about that. We obviously don't have an economy the size of China, but there are opportunities for us to work together. Oh, I was asked to say something about the industry as a whole. I think my time's up. I'd just like to say that I am chairman of a company called Australian Rare Earths. We have a project in South Australia. It's an ionic clay project. We recently announced that we've got an exploration target of 300 million to 1.4 billion tonnes. And we've done that exercise of demonstrating that we're not going to abuse the environment once we're in production. So I'll step down.
Thanks so much for that, Dudley. Now I'd like to introduce Gavin Beer. So Gavin is a metallurgist with 35 years of experience in the metallurgical, mineral and chemical processing industries in Australia, Asia and Europe. He has worked in metallurgical testing, flow sheet development and plant engineering, construction, commissioning and operations. Gavin founded Metchem Consulting, which specialises in metallurgical flow sheet development of rare earth deposits. Metchem has consulted to more than 30 rare earth companies since 2012.
Thank you, Sarah. Thanks to the AIG for inviting me to speak tonight. Also to our sponsors this evening. Firstly, an apology. My talk I'm giving is a rehash of a talk I gave earlier this year at the Alder conference. It was directed at a different audience, essentially for metallurgists. It is a general talk, however, on clay-hosted rare earths. So if I do start to get bogged down in some technical details, please forgive me, and certainly hit me up later on if you have some queries. Look, IADs, ionic adsorption deposits, operating in China, Myanmar, and Vietnam, as Dudley just mentioned. In the south of China, they're characterised by clay minerals, particularly kaolinite and halloysite. The REs in these types of deposits are essentially weakly adsorbed onto the surface structures. There's speculation with regards to the actual mechanism involved in that mineralogy. Some papers say it's hydrated layers. Some say it's actually substituted through cation exchange, much like perhaps gold is onto activated carbon. But ultimately, the important thing is that in these operations, the REs are released via quite simple desorption processes. Typically, ammonium sulfate is used. However, other types of solutions can be used. It's been found that you can actually enhance the kinetics of these desorptions in slightly acidic conditions, typically 2 to 4 pH. These deposits are generally characterised by low-grade REOs compared to their hard rock or carbonatite or alluvial type peers. However, quite often they will have a higher distribution of the heavy rare earths, samarium through to lutetium plus yttrium. The ones that we're particularly interested in of those heavies are the terbium and dysprosium. As Dudley said, they currently account in these regions for about 70 to 80% of the world's heavy rare earth production. Second type is what I'd call the weak acid or WAE clays, and they're characterised by minimal extraction with straight cation exchange. So these do require acid solutions to release the rare earths from their bound clay particles. Typically, you'll see these extractions occurring at pH 4, but generally in the operated mines, they get down to pH 1 just to improve kinetics. Again, speculation to exactly what's happening here, but it's most likely a combination of both this absorption and probably, I believe it's acid-soluble host minerals, such as carbonates and phosphates that I've mentioned. Now, there's some historical evidence of these types of deposits being processed in China, but in essence, they're fairly uncommon now, mainly due to increasing environmental constraints in China. They are also quite problematic in that once you start to go to fairly acidic solutions, you also dissolve, of course, the impurities that are in the gangue minerals, iron, aluminium, and silica, the main culprits. Then, when you start to look at reported clay-hosted rare earth deposits, what I call the other, and these are clearly just low concentration of your rare earth host minerals. So your classic refractory minerals, your phosphates, monazite, xenotimes, refractory silicates, and then you've got acid-soluble phosphates, fluorocarbonates. Quite easily checked by ionic desorption test, just using ammonium sulfate. And I do know that Lab West is becoming quite adept at testing these, so a bit of a plug for Lab West. They've got quite a good test for that at the moment, right? High acid consumptions, however, are and will be expected for this type of mineralogy, and your gangue minerals are really going to start to hurt you here. If you do have very little dissolution of rare earths, very likely your refractory rare earth minerals that are present at strong acid strengths will be the culprits. Okay, this is a general block flow diagram. I'll go through these steps one by one, and again, apologies if I do start to get a bit bogged down and technical, but in essence, essentially all of the operating mines follow clay-hosted deposits follow this type of processing route. In essence, you've got two types of processing. You've got a heap leach flow sheet. So this one, public domain information taken from the Makutu deposit in Uganda. You can get onto their website and see that, but in essence, you're mining and then produce heaps that you cycle through, and then the pregnant solution from the heaps are treated by purification and then ultimately making rare earth carbonate. Stirred tank is essentially your other option that's being looked at in the Western processes at the moment. Again, this one public domain from the Penco module. This is Aclaris. I was actually the QP for this particular one, and they're now into their final bankable study, just refining this flow sheet. In essence, the same principles are here, except they use stirred tanks. Post that, filtering, dewatering. You've got purification, and then you make a rare earth carbonate. Of interest, I don't know if I've got a pointer here, but if you look at the right, you'll see an awful lot of water streams kicking out to the right here. I'll talk about the challenges later, but these processes use a lot of water that must be managed. Aclaris spent a lot of money and time to ensure that they've got a completely locked water balance cycle. Doesn't come at a big capex. A lot of dewatering, very, very large thickeners, and also membranes for concentrating and recycling reagents. Here's an example in Brazil. This is the Serra Verde construction site. Again, public domain information. You can look this one up. Not a great deal of information. They have been constructing for a while. I believe they're still in commissioning phase. Apart from that, I can't tell you much else about Serra Verde, except I believe that they are actually using a brine solution, sodium chloride for desorption. Nevertheless, the flow sheet will be the same. Desorb the rare earths, purify, and then precipitate carbonate. Okay, so going through our block diagram, mining operation. Okay, now China has done in situ leaching. So this is a general block diagrammatic form of in situ leaching, taking advantage of topography. So in theory, it's quite similar to how you would in situ leach base metals or uranium, for example, honeymoon well. Get your percolation right, look for your aquifers, make sure that your injection wells and your extraction wells all line up. Once you've got the solution, again, purify and produce a rare earth carbonate. However, in reality, again, this is public domain. This is in Jiangxi province in China. So this was started off as an in situ leach. And once it started slumping, they found it was just cheaper and more effective to essentially hydraulically sluice the whole landscape. For those of you old enough to remember the Cowtails recycle project, very, very simple, except instead of hydraulically mining, they were using an ammonium sulfate solution. It does scar the land essentially long term, if not forever, and it actually hits home to Dudley's point there with regards to sustainable and appropriate use of our resources. Okay, ore preparation. So regardless of your mining technique, you need to get the ore ready to treat. So the in situ leaching, as I said, you've got to really ensure that your aquifer is well mapped. Preparatory work is undertaken. There is some questions with regards to the long-term fate of sulfates and ammonia injected into an aquifer or near an aquifer. So I won't go into that, but I'd suggest it would probably be fairly challenging to permit in many parts of the world, Australia included. Heap leach. Heap leaching has been well known in Australia and other countries, still used extensively, obviously, in South America with the copper processing. Advantages and disadvantages. So screening agglomeration and careful stacking required. Clays, by their very nature, are prone to swelling. Structural challenges can occur in heaps. So you can form agglomerates, but the long-term stability is another question. Then percolation, challenging and channeling considerations you need to take into account. Look, stirred tanks, belt and braces. Once you've got this material slurried up and into tanks, it's fairly well easy to design, but of course it comes at a significant cost. So Western stirred tanks, such as the examples that I've talked about, are considerably more expensive than the Chinese practices. So as these ionic clay deposits start to go through their various stages of engineering, the capex really does start to elevate, because low grades, if you want a decent output, you can need an awful lot of very, very large tanks and thickeners and filters. Leaching or desorption, essentially the same for this this presentation. Typically the conditions about 20 grams per litre ammonium sulfate. I talked about a slightly acidic adjustment there, typically sulfuric acid. And they generally provide quite fast desorption tests. Desorption kinetics under 15 minutes isn't unusual. Rare earth extractions are normally modest, reported in the 30 to 50% range. Although that said, I see some recent announcements from Meteoric. They're getting quite good extraction rates, much higher than that 50%. So that would be an interesting company to keep an eye on. Heat leaching, we talked about agglomeration stability. Tank leaching, it does require classification, screening, cycloning, filtering. I'll talk a little bit more about that later on, but again, challenging. And if you want to deposit this back into the pit after you've treated it and it's unlined, you need to make damn sure you get rid of the sulfates in particular, and particularly ammonia, because both are very soluble. I've mentioned impurity removal. In essence, this is where you're getting rid of these unwanted metals that you've dissolved. So your iron, your silica, aluminium, these are your typical culprits. So your raw solution, leach solution, unfortunately with these types of processes, they have very high impurity to rare earth ratios. So when you start talking about existing hard rock operations such as Mountain Pass in the US or Mount Weld, their concentrates, by the time they get to impurity removal, they are something like 1/10 or even less the ratio of impurities to rare earths. So what that means is that when you purify these solutions, you're using an awful lot of quite expensive reagent to purify them per kilogram of REO product out the back. That unfortunately means that you invariably have some loss of rare earths during that as well. Typically, ammonium bicarbonate is used. You can also use ammonium carbonate. It's quite an expensive reagent depending on where you are. Caustic soda and lime generally can't be used. The chemistry co-precipitates rare earths. Talked about removing the hydroxides of those elements. Aluminium and silica are problematic because they can form gels, and these gels in turn can rob the rare earths. And you need an awful lot of flocculant when you're dealing with fine clays and thickeners. Okay, through to the last stage now, and at this stage, essentially, this is where most of your rare earths processes, regardless of where they come from, start to converge. So this is your rare earth carbonate that then ultimately feeds into a rare earth separation plant downstream. Typically, again, using ammonium bicarbonate, although you can use at this stage possibly sodium carbonate to precipitate. Dudley talked earlier on about calcium, but also aluminium has to be very low when you start to send these to separation plants. Chinese spec is 0.1%, but specs I've seen out of Europe require much lower. So you really need to get this rare earth carbonate pretty clean. As I said before, your ratio of rare earths to impurities is high, so I wouldn't be surprised if you need to have a couple of cracks at it. Purify it, redissolve, and then purify again. Or take some extra losses of rare earths and recycle them back. The good news is radionuclides generally aren't a problem because they're quite low in these deposits. However, watch the decay daughters. And by that I mean that the thorium and uranium decay chains have other chemicals that kick in. And the final product is essentially just dried and bagged for export or sent to a refinery, it's the SX refinery. How am I going for time? Do a couple more, right? Look, a quick breakdown. I think you'll have a copy of these presentation, again, public domain. This is talking about OPEX, which is pretty important here. You can see that on this slide here, the large circle on the shows that the process makes up about 54%. This is for the Aclara deposit. And that 54%, the subsidiary of that, about 18% is reagents and suppliers. So reagents, again, is, as Dudley mentioned earlier on, is quite a large portion of the costs. Another public domain information here is Makutu. Here, the reagents are a bit higher. In actual fact, once you delve into it, you can see that the way that they account for their water and their tailings actually balances it out. So you can actually equate those reagent costs fairly similar between the two. And of reagent costs, you can see here that your purification reagent, in this case ammonium bicarbonate, for the case of Aclara, is the lion's share, even more than the ammonium sulfate. And again, RO water here, which is included in the reagent cost, is significant. So final commentary, reagent costs somewhere between 10 to 35% of the OPEX. Carbonate, very expensive. You need an awful lot of flocculant and also water recycle to deal with these. And the nanofiltration, which Aclara is using, it is off-the-shelf technology, but the capex of it is significant. Final commentary on capex, stirred tank reactor design, very large tanks for required, as I mentioned earlier on, offset by fast absorption, and huge plate and frame filters. So the needs in terms of capex will be very significant. Heap leach, you can get by with the lower capex, but of course it comes with an increased risk. Agglomerator and stackers, of course, need to be included. I'd just like to talk about the assumed revenue. Quite often you'll see, not just in this, but other companies, there'll be a simple, maybe a paragraph or a couple of pages in a scoping study at best saying that we've gone and looked up on metals prices and we looked ahead and we just simply discounted our basket price by a certain percentage. In essence now, offtake terms are becoming more widely known from Europe, from Japan and also from China. Typically, in a carbonate, you'll only be paid for the 6 rare earths, cerium and lanthanum, because they're common, and PRND, TB, DY, the magnet metals. Terms generally will be a single term, so a very small percentage of lanthanum and cerium, and generally a very high percentage of PRND, TB and DY. All of those other exotic heavies, in essence, you won't be paid for, because they'll justify that to say that they need to do hundreds, if not thousands, of separation stages downstream. So if you are evaluating a deposit, I would suggest you look at those magnet metals, look up your spot price, and assume conservatively full value for those, and give yourself nothing for the rest. So if you're doing a back of envelope calculation, that's probably going to let you know how much money you've got in the queue before you start spending money. Okay, last slide, some take-home thoughts. We mentioned earlier on, some simple lab desorption tests can really provide a no-go assessment as to what sort of mineralogy you've got. How much reagent are you using? If you really need to throw a lot of acid at this, and also your ammonium sulfate, and it starts to get sort of north of 10% of the basket price of those 4 elements, then in essence, what the studies are telling us now is that you're going to be up for a real challenge. So again, there's a good back of envelope to say, if you don't have enough revenue to pay for your reagents, assuming a 10% of total OPEX, then you're going to be struggling. Radionuclides are probably going to be okay, but if you do have uranium in the ore, just keep an eye on the decay chain, particularly the actinium. The last thought I'd give you just before I leave tonight is that everybody has been quite excited about what the Chinese have done. And I'd ask you to question is the Chinese rare earths produced from their ionic clays equivalent to our Western business model? And quite rightly, as Dudley said earlier on, the integration between state and mines, and in particular between the support infrastructure, the reagent suppliers, the mining companies, and in particular the downstream companies going to oxides, magnets, and final products, are more than likely to be accepting these rare earth ionic clay deposits operating at a loss. So just because they're operating does not mean that they're going to. I'll conclude on that one. So I'll invite you later on. I think we're taking questions later in that.
Gavin from Southern Geoscience, I'd like to call Ivon Wallace to the lectern. Ivon is a principal geophysicist at Southern Geoscience Consultants. She has 20 years of experience in mineral exploration projects across Australia, Papua New Guinea, and further afield. She specialises in the integration and interpretation of geoscience data to identify and further targets for mineralisation.
Good evening, everybody. And tonight I'm going to talk about the production of working geological maps for use in minerals exploration targeting. So a step before the kinds of topics that we've been touching on already. And to do that, I'm going to focus on the use of aeromagnetic data at various scales using a rare earth case study from Tanami in WA. I'll just start by thanking PPW for their permission to present the data and my SGC colleagues for all of their input. So working geological maps, we're talking about the kinds of base maps that we want to use for exploring, and they need to be fit for purpose. So they need to enable the identification of key exploration criteria relevant to the required commodities, and they need to do that in the context of the geological setting. And to be really effective, base maps need to be of high quality and preferably consistent across their extents in terms of their resolution and the quality of the data that informs them. Airborne magnetic surveys we apply routinely as a primary geological mapping tool by capitalising on the ability of the magnetometer to sense the 3D distribution of magnetite minerals in subsurface rocks. And on the right-hand side there, I've got the example of such a working geological map from the WA side of the border in the Tanami. And then on the next slide, that's another similar kind of type of map, different source on the Northern Territory side of the border. So modern aircraft and refined geophysical instrumentation provide us with a really reliable and highly sensitive data set. And we can sense even really, really tiny amounts of magnetite minerals down to as little as 0.0003% magnetite. In tandem with that, we've got very well developed survey specifications for line spacing, flight height, drake, and other technical considerations. And that all enables us to have really super consistent acquisition of data with good spatial sampling and minimal artifacts. And that's all been in place now for several decades, meaning that historic data can also provide significant value to exploration projects at all stages, and it's often available on open file at no cost. So costs of new surveys vary a bit with mineral demand from year to year, but in general, they've remained very small since the 1970s compared to other activities which have increased in price, like geological mapping, geochemical surveying, and other geophysical survey types. So we like to say that airmag cost about $10 a line kilometre in the 70s, and it costs about $10 a line kilometre today. So the use of aeromag data essentially follows the same principles as for geological mapping. So we combine an understanding of the underlying geological processes with the observed aeromagnetic signals that are representative geological features in the subsurface. And to do that, we use a two-phase process. Oh, that hasn't worked, sorry. I don't think I can allow it. In reading mode, I think. Check again. Okay. All right. So we first will complete an objective observation of the aeromagnetic data, which is analogous to making observations in the field notebook and on the field map. And then that's followed by a much more subjective interpretation phase where a working geological map and targets are developed for us to then have context for developing hypothesis for further focus. And to maximise the geological targeting value from the data, we need to work at a minimum of 2 scales. We like to work down from a wider context down into an area of focus, and we'll illustrate that using this case study. So exploring for rare earths in the Tanami, we've got hydrothermal conformally related rare earth deposits, curie deposits, containing mineralization dominated by xenotime at the by xenotime, which is an yttrium rare earth phosphate mineral. And that's been discovered at the Browns Range Dome in the northern Tanami with a resource of more than 80,000 tonnes total rare earth oxide. Here at Browns Range, we've got the phosphorus bearing acidic fluids. From the overlying Gardner sandstones in the Birindudu basements. Mixing with fluids derived from the much older Browns Range metamorphics. And that happens in fault zones that transect that unconformity, enabling that extensive xenotime precipitation to veins and breccia. And then further to the south, the potential for extensive urine mineralization was identified by PBW in an analogous setting along the Watts-Costella trend. That's about 18 kilometres long. And here we've got mineralization disseminated in stratiform horizons, veins of breccia, found close to a regional unconformity, which again lies between the older basement rocks of the Kilikili Formation and the overlying younger Parji sandstone. So let's have a look at the aeromagnetic data over PBW's greater tenement holding. And this is a merge of both existing and newly acquired survey data, and it has predominantly 50-metre line spacing. So this is really high resolution data, and it gives us the opportunity for observation, interpretation and targeting at a host of scales, all the way down to a maximum zoom in, if you like, of about 1 to 5,000 or prospect scale. The left-hand side is an RTP amplitude image, colour sun-shaded, and the right-hand side is an unshaded grayscale derivative image. So we're going to work initially at a stepped-out scale of tens to hundreds of square kilometres in kind of aerial size. This would be a district or maybe a tenement package. And we like to analyse the data at that scale to get a broad understanding of the geological architecture, maybe some sense of the geological history, and allow us to infer key drivers for mineralisation. So aeromag data can map both lithology and structural architecture, and lithology-wise, it includes delineation of major contacts here, such as those between the magnetic Frederick and Sweet granites and the surrounding sediments. Phases within the granites as well, and major intrusions such as dikes and sills, which you can see intruding the sedimentary sequence. Along the way, we often will identify odd-looking, maybe subcircular oval type magnetic anomalies which don't fit the general geological pattern, and they might represent some sort of anomalism or important intrusion, so we note those as we go. And then within the weakly to non-magnetic sediments of the Tanami group, low contrast sediments, and also within the overlying Parji Gardner sequences, we can map out subtle linear features representative of weakly magnetic bedding. And these kinds of features are of the order only a few nanotesla. So structural observations through the area we can make by identifying breaks, offsets, discontinuities, and other disruptions to the magnetic patterns, and interpret those as major through-going corridors, district prospect scale faults, and other local scale fractures. And within the Tanami group, we can infer local scale folding using form lines in the magnetic fabric. So interpretation of the data here has been initiated with this sort of regional sketch, if you like, capturing those large scale features. And we can start to note the evidence for geological criteria, for favourable mineral settings in terms of looking for complex structural sites, favourable lithology, broad scale anomalism. And that sets us up then to continue this work down at the next scale. So here we're going to analyse the magnetic data at 1 to 50,000 scale, kind of bushwalk map scale, and integrate that with the available outcrop mapping, which in this case was horribly limited to the GSWA 1 to 100,000 scale mapping. Great mapping, hardly any exposure, as you can see there. And so during this kind of process, we find that in these areas of limited prior exploration, especially those undercover, that, which is a large portion of this area, we'll rely more heavily on magnetic interpretation to drive the exploration focus. Whereas in areas where we might have more exposure and other prior work, drilling and so on, the compilation process is more that of an integration of the magnetic data. So the left-hand side image shows the full aerial extent of the work at the scale. The right-hand side is a zoom in of the orange box. And at this scale, it's possible to map out the magnetic form lines within that dead bullet formation, Stubbins formation, at surface as well as undercover, as well as within the Kili formation. So that's the Tanami group formations and the younger overlying sediments. This then aids the interpretation of distinctive anticlinal folding within the Tanami group and allows us to infer contacts between the various sequences. We can distinguish major through-going structure corridors from secondary faults and from more minor faults and fractures. Differentiate also the granite contacts and the magnetically distinct mixed zones around the granite rim, and generally overall refine various other features across the map. And importantly, at this scale, it's now possible to interpret the individual Pargi sandstone and Gardner sandstone sequences, as well as sequences within the Pargi sandstone, and the unconformable Watts-Costella trend between the Pargi sandstone and the older Kili formation. And we also note that we can see a similar unconformity to the north at Larangani. So the Larangani unconformity and the younger sets overlying the older sets. That's the unconformity down here. In terms of potential areas of exploration interest, these are going to be strongly guided by structural setting, with that Pargi sandstone Kili formation unconformity being the highest priority for rare earths. We can also look at the airborne radiometrics data, which is acquired at the same time as the AirMag. We look for anomalous uranium and thorium zones that we can outline as possible indicators for rare earths. And so now that we've set up that geological context and we've identified some key drivers for mineralization, we're going to focus in on the high priority areas. So we zoom in now at 1 to 10,000 scale, so I guess prospect scale, along that Watts-Costella trend. And again, we'll integrate with the available 100,000 scale outcrop mapping. We didn't have anything else at this point in time, unfortunately. In terms of mineralization, we know that the Huri deposits typically have a small aerial footprint of a few hundred meters in strike length and are around 10 to 30 meters in width. So at that kind of scale, 1 to 10,000, we're starting to approach the full resolution in the 50-meter line space magnetic data set, but there's ample room there to complete a pretty detailed analysis suited to that target type, which builds on the context that we set up by the larger scale work. So the level of focus at that scale then allows for really detailed capture of very subtle magnetic features, such as bedding within the sediments and faulting, and that's across the Kili and the Pargi, the Gardner sandstone. And that includes structures which intersect the unconformity. And that leads us on to points of interest of providing potential focus for the mineralisation. We do have in the data some uncomfortable looking high frequency noise, which is due to near surface sources. But with enough time with the data, we can deal with that by a combination of reading through these patterns to the underlying bedrock signature and or referring back to our stepped out context as well. So in terms of alteration indicators, as before, we can identify obvious through to very subtle radiometric anomalies which don't fit the general geological pattern. So that's in the context of what we expect the lithological pattern to be. So following this work, PBW undertook various activities last year, including surface geochem. And at Watts Rise, the working internet has highlighted an array of east, northeast, and northwest trending structures, including the inconformity, that seem to be near coincident with yttrium soil anomalism and uranium anomalism from radiometrics. And again, at Castella, there appears to be an association between soil anomalism and intersecting structures. Just to wrap up then, in the Tanami, we use this broad structural and lithological understanding at the regional scale, using the MAG surveys and follow-up analysis at district scale that allowed for reduction and refinement of the search space, anchored by whatever we had available, which in this case was sparse but useful outcrop mapping. And then at the Watts Castella trends, we carried out this highly detailed interpret of subtle structures and alteration related anomalism, which has helped with targeting for further mineralisation. Other activities of note that PBW have carried out include ground radiometrics, which did help to refine the responses that we'd seen in the airborne reds and hone in on those target areas. They've also collected very detailed ground gravity data and carried out 1,000 to 2,500 mapping. So there's done a little bit of drilling. So there's a lot more to go at now in terms of going to the next step, working up those exploration maps and the target sets and formulating their exploration plans going forwards. And that's it.
Thanks so much for that, Ivon. Our final presenter for the evening is Richard Granini. Richard commenced his career in mineral exploration with BHP Minerals in 1987, working in teams focused on the discovery of base and precious metal deposits across Australia and North America. His experience since then includes time working as director of the Northern Territory Government Geological Survey and being the executive management of Arapura Rare Earth. Richard is an executive director of Heavy Rare Earths Limited, which listed only 13 months ago. Over to you, Richard.
Thank you very much for the introduction. Appreciate it. And for the opportunity to speak here this evening. And also, like in previous meetings, I'd just like to thank all the sponsors, including Lab West, that we put maybe 95% of our assays, with the exception a little bit through ALS. So thanks to everyone here for attending. Rare earths are very topical at the moment, have been for around, I guess, the last 18 months, but it's becoming more and more difficult from what I can see to raise money for rare earth projects at the moment. There's a little bit of fatigue around rare earths. And I guess I'm here tonight to try and get across to you the sorts of progress that we've been able to make in listing a rare earth company about a year ago. So we've made, I believe, some good progress. Not as fast as what I'd hoped. I guess at the commencement, when we did list the company, my feeling was, and I'm an executive director of the company, the only employee, as it turns out, I thought that within about a year, we might be able to bring forward a project that has some legs, that might have a chance for development. I think it's going to take a little bit longer than that. It's going to take us about 18 months to get to that point. And so we're 12 months into that journey. Okay, what do we look like? The main project that we're developing in the company is Caolinia down near Esperance. At the time at which the company was listed, work had already happened prior to listing, and the company listed with a small mineral resource, and that remains today. We have other projects there as well. The second project that we had listed, or we came to market with, was a project in the Northern Territory called Duke. Caolinia in Western Australia is a clay-hosted deposit, hosted with saprolite. Duke, we're looking for heavy rare earth enriched zenotime Browns range style, which is for the previous speaker. And we have a lot of things going on now to get to our 1 year or just past 1 year. And I guess the nearest term share price, what's the word I'm looking for? Something that's going to hopefully move our share price in the next little while is mineral resources. We're actually going to be declaring some mineral resources probably about the end of this month, and an exploration target for Caolinia. So they're the sorts of things, the near-term catalysts that we're looking at. There's only myself, as I said earlier, as the only employee, but I heavily lean on 3 consultants, 2 of which are in the audience tonight. Gavin Beer on the metallurgical side of things, Andy Wild in geology, geochemistry, and also his knowledge around uranium systems. I'm finding that quite interesting as it relates to rare earths. And David Ross, who isn't here this evening, unfortunately, he was the vendor of the Caolinia project into the company. We won't worry about corporate snapshots. That's more a promotional talk. Let's start talking about Caolinia. I might just can't see anything on the screen, and I'd like to be able to see what I'm talking about here. Okay, it's 100% owned by heavy rare earths. It's on a land position of 250 square kilometres. That's quite small compared to many of our peers in the district, but my belief is that we really need 2 things to be able to demonstrate to the market that we've got a real rare earth project that can be possibly brought to development. Firstly, we need enough rare earth sitting in the ground, given the grades that are usually involved in these clay-hosted deposits. And in our case, we've got 625 ppm in the ground in a resource, 28 million tonnes of inferred resources. So you're going to need a lot of rare earths to be able to produce something that is going to be noticeable to the market, because someone's going to have to come in and fund this at the end of the day. And if you're starting with 1,000 ppm in the ground, you're going to have to produce a lot of throughput through a mill, through a process plant, to produce a reasonable amount of rare earths for sale, and for someone to come in via an offtake agreement to be able to help fund the project. Okay, so we're going to need something of the order of 1 billion tonnes of material. Go back to the sorts of numbers that Dudley was talking about earlier in his exploration target. But my belief is that you're going to need something of the order of 1 billion tonnes of material of the sorts of grades that we're dealing with, or even up to 1,500 or 2,000 ppm in the ground, to be able to push that through and to produce enough rare earths. Okay, that's the first thing you're going to need. The second thing you're going to need is a very, very efficient process. Now, we can't do it like the Chinese. We heard that from Gavin. Okay, so those sorts of techniques are not going to be available to us. It's going to be more expensive to do that, to produce rare earths from these styles of deposits in Australia. So we're going to need a very, very efficient process. My background tells me that I should be concentrating on OPEX. Okay, you can raise money depending on the sort of amount of money that you're going to raise to build something, but you won't be able to raise money, I don't care what it's going to be, if you can't operate profitably. Okay, so you're going to have to come up with a very, very efficient process. So they're the 2 things that we're concentrating on as it relates to Caolinia. As I said earlier, we brought a small or a modest resource to market. You'll see on that map there, there's a couple of areas called Caolinia North and Caolinia South. It occupied about 1% of the total area of our tenements, okay, which is about 250 square kilometres. We've since drilled another 15% of the tenement. You can see all those drill holes down in the bottom right-hand corner of the tenement there. Those are drilled at around 400 by 200 metres on a grid, okay? How did we target? Well, we of course started from our existing resource, and felt that the best way was obviously going to be branching out or stepping out from existing resources. We did have access to some airborne electromagnetics in the area flown by previous explorers, and you can see the grid-based drilling in the very bottom right-hand corner begins to break up a bit. That's because we had access to airborne electromagnetics, and we could see how that was mapping those conductive saprolites in the subsurface. What we can't tell, of course, is what the grade's going to be like. Okay, so that's still a bit of an unknown before you start drilling, obviously. Okay. In addition to that, we decided that not only to build our resource base, and what we're hoping to be able to put forward is something more than 100 million tonnes at a first go. We also decided it'd be a good idea to start drilling some holes, some far field holes from the resource, to be able to begin to demonstrate, hopefully, to the market that we do have the possibility of several hundred million tonnes on our land position. Okay. We're at a very advanced stage of putting forward our new mineral resources. This is a cross-section across the drilling area. You can see there, showing block grades. Once you start zooming in, you can start to see some of the grades. We drilled quite high grades in some areas, way above our average resource grade of 625 ppm, up around 4,000 to 5,000 ppm in places, generally around the 700 to 800 parts per million. So they're the sorts of numbers I'm expecting in new resource. So there's a couple of cross sections. Mineralogy, well, this is where it starts, the rubber starts hitting the road. There's a couple of SEM images. What we generally see are sub 20, 25 micron rare earths sitting in kaolinite lattices. Okay, that's generally what we see. But those rare earth bearing minerals are monazite and xenotime nearly all the time. Now, monazite and xenotime are acid resistant. Okay, however, if we go to the next slide, we can begin to see, and I won't take this through in any detail, but we begin to see extractions of rare earths in hydrochloric acid up to around 80%, 80+%. So that's telling us that there's something else in the matrix that is coming through into solution. It's not the monazite, it's not the xenotime, okay? There are other mineral species, or there's other rare earth species coming into solution, and we're just not across exactly what that is. We have partnered, or as part of the RSC or Merriwa project characterisation of rare earth deposits in Western Australia. We're hoping that they'll bring forward more evidence as to what we are dealing with there insofar as those rare earths coming into solution. A couple of other things there. Our screening work has allowed us to double the grade coming into leach in 42% of the feed mass of the saprolite of the feed mass. We're getting 81% recovery of magnet rare earths going to the fines, a sub 25 micron fraction. 82% of those rare earths are coming into solution using hydrochloric acid. We've used other reagents, they just don't work as well. So all we're trying to do here is maximize the revenue in bringing as much rare earths as we can through to solution, and most importantly, minimising the consumption of that acid. So that last column there tells us that we get an average consumption of 18 kilograms of hydrochloric acid per tonne of fines material, which is actually quite a good outcome, actually. So what we're looking to do is try and find more of that material. That's 8 composites that you can see there. We had 13 composites, 5 didn't work so well. In other words, too high acid consumption, too low rare earths coming through into solution. So we just set those aside. We're looking for that form of material in our project. And so we've commenced a variability study, and you can see on the left there, the colours aren't all that good, but the orange, we've got orange up there, which is there are 55 samples that we've collected, 6 metre composites, and that's 55 of them that are going to strategic metallurgy for the next round of variability studies to build on our blue ones, which are the 13 that we've used to generate the previous results. In addition to that, and you would have seen that little block diagram from Gavin Beer's presentation, we're looking to, we're sufficiently encouraged by the results to date, the metallurgical results to date, to look at the downstream aspects of our flow sheet as well. So we've got liquors prepared from two of our preferred material types to be able to produce a rare earth carbonate, samples of rare earth carbonate. The impurity removal step, of course, is the key step here. We need to see low consumption of the appropriate reagent. That could be lime in this case, as we're working in the chloride media. It's probably going to be caustic soda. We'll see what happens, but we need to see low consumption of that reagent to be able to produce a rare earth carbonate. I'm not interested in producing a rare earth carbonate that is not going to make us money. Okay, so that's coming. And very quickly, I'm just getting wound up here. The other two projects that we have on the go, the Dew project in the Northern Territory, we've completed a soil sampling program there. Those assays are sitting at Lab West right now, so we'll start seeing some results probably next month. And that's a Brown's Range style target there. And finally, we've also picked up some ground in the Midwest region of WA, looking at rare earths in paleochannels on top of Archean granitic basement. And you can see on the right there, the WASANT paleochannel map, which came in quite handy for some of the early part of the project generation work that went into that. And that was Andy Wallace's work. So I'd like to thank him for that. And I think that's pretty much it for me. So any questions, please come and grab us.